Greetings everyone and welcome to section 7.3, diagonalization. Last time we looked at a matrix A, 3's negative 4, negative 1, 0, negative 1, negative 1, and 0, negative 4, and 2. And we determined that it had two eigenvalues. The first one was lambda equals negative 2, which had a corresponding eigenvector of 1, 1, 1, and lambda equals 3. Okay, and lambda equals 3 was a multiplicity 2 in the characteristic polynomial. And its eigenvectors were 1, 0, 0, and 0, negative a quarter, and 1. Now, since this 3 by 3 matrix had a complete set, 3 linearly independent eigenvectors, we called it diagonalizable, okay, or non-defective. If it had 2 or fewer, it would have been a defective matrix. Okay, at this point, what I want you to do is I want you to make the following two computations. Take the matrix A and multiply it by V1, V2, and V3, where V1 is the eigenvector for lambda equals negative 2, and V2 and V3 are the eigenvectors for lambda equals 3. Okay, and what you'll see when you do this matrix multiplication is you'll get a matrix that looks like this. Okay, and as a second related problem, I want you to take the eigenvectors here for the matrix, okay, and multiply it by this diagonal matrix. Now notice what is happening here. I'm taking the lambda, the first eigenvalue, negative 2, in the upper left-hand corner, column 1, and I'm multiplying it, this matrix here, by this matrix where the first eigenvector, or the first column, is the eigenvector that corresponds to negative 2. This eigenvector corresponds to 3, and this eigenvector corresponds to lambda equals 3 as well. And what do you observe? Well, when you do this computation, you get this same matrix right here. So if I take A and multiply it by this matrix, we'll call S. Okay, and it's the matrix of eigenvectors. We get that matrix S times the matrix D, okay, where the matrix D is a diagonal matrix with the eigenvalues along the diagonal. So just to summarize that, if we call S vector 1, vector 2, and vector 3, then we observe that AS equals SD, where A is the given matrix that is diagonalizable. S is the matrix whose columns are the complete set of eigenvectors of A, and D is a diagonal matrix with A's eigenvalues carefully chosen along the diagonal, carefully chosen so that it corresponded with the corresponding eigenvector. All right. So naturally, when things like this occur, you ask yourself, is this by accident or is this by design? Okay, is this unique to this problem, or will it happen for others? Okay, and here's your answer. Here's a theorem. Theorem says let A be an n by n. Okay, this is n by n. It looks like me writing non, but it's an n by n diagonalizable matrix with eigenvalues lambda 1, lambda 2, all the way up to lambda n. And eigenvectors v1, v2, vn. Of course, eigenvector v1 corresponds to eigenvalue lambda 1, and eigenvector v2 corresponds to lambda 2, and so on. If you let S be the matrix whose column vectors are eigenvectors, and D be the diagonal matrix who along the diagonal is lambda 1, lambda 2, all the way to lambda n, where each of the lambdas are selected carefully to match up with their corresponding eigenvector, then what you will observe is this diagonal matrix D is equal to the inverse of S times A times S. So that's a fact that we can prove. We won't prove because it's not necessary to prove it, okay? But we can take the result from it, okay? So this definition of A being diagonalizable when it has a complete set of eigenvectors is somehow related to this diagonal matrix D, which is the eigenvalues of A. Now, I'll offer you another definition. Okay, I'm sorry that there are so many terms here, but we have to talk about each one of them. If you let A and B be a square matrix, okay, A is similar to B if there is an invertible matrix S such that S inverse AS is equal to the matrix B. Now, how is this definition related to the theorem above? Okay, well, what's different? Okay, here in the definition, we have B, A is similar to B. We'll write it this way, we'll write it in English. A is similar to B if B is S inverse AS. And the theorem above said if A is diagonalizable, then D is equal to S inverse AS. Well, the difference between this theorem and the definition is that D was very specific here. It was a diagonal matrix of eigenvalues. And S has columns of eigenvectors. Okay, but these two, the definition and the theorem, are related to one another in the sense that you can look at and say that by definition, if A is diagonalizable, then A is similar to D, the diagonal matrix of eigenvalues. Okay, so if A is diagonalizable, then A is similar to D, a diagonal matrix that has the eigenvalues of A along the diagonal. Okay. In general, if A and B are similar to one another, it's not necessarily true that B is a diagonal matrix. A and B can be similar, where B is not a diagonal matrix. It's just that there exists some S that's invertible, such that when you multiply S on the right and S inverse on the left, you get the matrix B. Okay. One thing that I'm going to note, and I'll write it here in red, we talked about A similar to B if B is S inverse AS. Okay, if I were to multiply on the left by S and on the right by S inverse, I would get SB S inverse is equal to the identity matrix times A times the identity matrix, which is A. And so A is equal to SB S inverse, okay, where S is the inverse of S inverse. So you can equivalently think of this as being B is similar to A. So if A is similar to B, then B is similar to A. So it works both ways. All right.